This is Senior Algebra, Section 4.1, Solving Systems of Equations by Graphing. So today we're taking a look and we're going to be given an order pair, see if it's a solution, and then we're going to be solving systems. System is 2 or more equations, and we're going to be finding solutions to that. So I'm going to check if 4, -1 is a solution to both equations. So I'm going to plug in 4, and I'm going to plug in -1. And then I'm going to solve it for the first equation. When I do that, I get 20 plus -6, which is 14. I get 14 equals 14. That's true. It works in the first one. I'm going to plug it into the second one. -2 times 4 minus 5 times -1 equals 14. So I get -8 plus 5 equals 14. We know that is not true. I get -3 equals 14. So what can we say? We can say that 4, -1 is not a solution to the system. It doesn't work in both of them. In order for it to be a solution to the system, it has to work in every equation. In example 2, now we're solving the system by graphing. So we're going to graph each of the equations, and we're going to find out where or if they intersect. Where they intersect is the point where what they have in common, where both things are going to be true, because anywhere on the line is true. But I want to find a point where it's true for both of them. So I'm going to get y alone in the first one here. I'm going to subtract 2x. I'm going to divide by -3. I get -3 plus 2/3 x. I'm going to do the same thing with the second equation. Move the x over. 2y equals 8 minus x. I get y equals 4, and then what? Plus negative, and that's a plus -1/2 x there. So now I'm going to graph both equations here. So I'm going to graph y equals -3 plus 2/3 x. Graph looks like that. I started at -3, I went up 2 over 3, up 2 over 3. I'm going to do the same thing with y equals 4 minus 1/2 x. So I'm going to start at 4. On the y-axis, that's my y-intercept. I'm going to go down 1 over 2, down 1 over 2. When I go down 1, that's where the negative comes in. Over 2 means I'm going to go to the right 2, because that's a positive 2. Notice the slope is going down and to the right, which we'd expect with a negative slope. So I find that 6, 1 is going to be the solution. It works for both of them. So now I'm going to do the same thing with example 3. I'm going to solve for y and graph it. Are there ways to graph it? Sure. For me, I'm going to always get it in y equals form. So I solved the first one, I got y equals -4 plus 3x. I solved the second one for y, and I get y equals -6 plus 3x. At this point, I'm going to graph both of the lines. So I'm going to graph each of these lines. First one, y equals -4 plus 3x. I'm going to start at -4 and go up 3 over 1. Excuse my lack of a straight line there. Second one, y equals -6 plus 3x. So I'm going to start at -6, and I'm going to go up 3 over 1. When I do this, I see that I'm looking for the intersection, but in fact these don't intersect. The lines are parallel. Remember, parallel lines, slopes are the same. So what could we say? If there is no place that they intersect, what would we say? We say, well, there is no solution. There's nothing that would work. So in example, so in part B here, we're going to do the same thing. We're going to graph each of the lines. We're going to get y alone. So in B, we're going to work to get y alone here and graph each of the equations. So in B, we're going to work to get y alone. We're going to graph each of the equations. So we get negative 10y equals negative 4x plus 16. And I'm going to divide each side by negative 10. When I simplify, I get y equals negative 8/5 plus 2/5 x. I'm going to do the same thing with the other one. So at this point, I'm going to graph it. I'm going to start at negative 8/5 and go up 2 over 5. So I'm going to do the same thing now with the red equation. I'm going to start at negative 8/5. I'm going to go up 2 over 5. Now, what I should notice is that, I get the same line. If I look at the equations are the same. Same slope, same y-intercept. Since they are the same, what are the solutions? Well, there are infinitely many solutions, because there's infinitely many points on a line here. Now, is that the same as saying their solution is all real numbers? No, it's quite different. We say there are infinitely many solutions. Do not say all real numbers, because all numbers will not work in the equations. There's only certain ones that will work, but there are infinitely many number of those. So we have the three cases for solutions. One solution where they cross, no solution where they don't cross, when we have parallel lines and they don't intersect, and then infinitely many where it's the same line. So when they exactly one point they intersect, we say the system is consistent, meaning that it does have an answer, and the equations are independent. Independent means they are different. When I have parallel lines, there's no solution, so it's inconsistent, but the equations are still independent. They're different equations. And then the last one, we have parallel lines. The system is consistent because there is a solution. We will not be writing it in set builder notation there as shown, but we could, but we won't in this class. But we do say the system is consistent and the equations are dependent. Equations being dependent means that they're the same. Independent, different from each other, dependent, the same in this case. So an example for without graphing, we want to state the number of solutions here. And we want to look at the slope, we want to look at the y-intercept. How many solutions there are going to be. So in A, I'm going to get y alone in each of them and then look at them. So when I get y alone in each of them, I get 2/3 x minus 7/3 and 2/3 x minus 5/3. In this case, the slopes are the same. two lines have the same slope, we know that they are parallel. But the y-intercepts are different. What does that mean? It means they're not the same line. So we say they have parallel lines. What does that mean? How many solutions? That would be a no solution. And when it's no solution, we say that the equations are inconsistent, meaning there is no answer, there's no solution, and independent, because the equations are different. Again, notice when I look back, oh yeah, parallel lines, they don't cross, same slope, different y-intercepts. So I'm going to do the same thing in B and C. I'm going to take a look, I'm going to get them in y equals form, I'm going to look and compare the equations. So on the first equation, I got y equals 1/3 x plus 2/3. In the second equation, I get y equals 1/3 x plus 2/3. Same slope, same y-intercept. What does that mean? It means the lines are the same. Okay, so if it's the same lines, we say that there are infinitely many solutions. We can also say that the equation or the system is consistent, meaning that there is a solution. The equations are dependent, meaning they're the same equation. So we say consistent and dependent. So in C, I'm going to do the same thing. I'm going to get y alone. I get y equals 2x plus 11. In the second one, I get y equals negative 6 plus 3. The slopes are different. Well, slopes are different. That means that they will cross only one time. That means there is one solution. We say that the system is consistent because there is an answer, and the equations are independent because they are different.